All right, we're going to be learning about forces and Newton's laws today. This is self-paced, so if any time you want to pause or rewind, feel free to do that. Okay, we're going to talk about inertia first. So inertia is what I was trying to demonstrate when I was pulling tablecloths out from underneath dishes, and when I was dropping the dice into the cup, and when I pulled the money out between the bottles and all that. I was trying to demonstrate the principle of inertia. And inertia is Isaac Newton is credited with discovering or first explaining inertia, I should say. And he explains it in his first law, the law of inertia. And it simply states an object at rest remains at rest, and an object in motion remains in motion unless it's acted upon by some force. And an object with balanced forces, so if like one thing is pushing on one side and another's pushing on the other, it will stay at rest, or it will stay in constant motion. All right, so now how can we measure inertia? Well, inertia is the tendency of an object to maintain its state of motion. And imagine applying like a small force to a ping pong ball, right? Just like kind of just like push it with your finger, right? A 10 Newton force, we'll call that. And what would that ping pong ball do as you were pushing it with your finger? Okay. Now I want you to imagine applying the exact same force to a bowling ball that's at rest. And what does a bowling ball do, right? I think you've probably imagined that the ping pong ball, as you're pushing it, just goes real fast, right? And a bowling ball is much harder to push, and it's slower to get going, and it's slower as it rolls. So that means like the more mass an object has, the more resistance it has to change its state of motion. And there's a direct relationship there between how hard it is to move something and how massive it is. And you know this if you've ever ran out of gas and had to push your car, or if you've ever like pushed a bookshelf across the floor. Well, what's the best thing to do if you're going to move a bookshelf? Take the books off first, right? All right, so therefore mass is the measure of inertia. And mass, is the amount of stuff that makes up an object. It does not vary with location. So you go to the moon or you stay on Earth, you have the same mass. It's your weight that changes. Forces. So what is a force? A force is actually exactly what you think it is. It's a push or a pull. If you want to be more specific, you could say it's an interaction of an object with its environment to change the object's motion. Now, forces are measured in newtons. And a newton is like a combination of more than one unit. And you're used to combinations of units, right? Like, for instance, we say, we'll say like velocity. The unit of velocity would be meters per second, right? Or acceleration would be meters per second squared. So Newton is it's such a big combination that we just say Newton instead of saying what it really is. And yes, we named it after Sir Isaac Newton. But you see, an actual Newton is a kilogram meter per second squared. That would be a mouthful, and it would be difficult to write all the time. So we just write down N for Newton. One way to remember that it's a kilogram meter per second squared is a Newton is actually just force is just mass times acceleration. And we'll talk about that later in these slides. But, well, kilogram, that's our SI unit for mass. And meters per second squared, that is our SI unit for acceleration. So it makes sense that kilogram meter per second squared would be a Newton. There are two general categories of forces that are touching and forces that are not touching. So the ones that are touching are contact forces. This is probably the one you typically think of a force, right? It's a force that arises from physical contact, like friction, normal force, pushes, pulls, tension, etc. And don't worry, I'll teach you what a normal force is later. A field force, this is a force at a distance. A field force exists between two objects without physical contact. And that might sound like magic, but you've seen that in your everyday life, right? Gravity is a field force. You are attracted to the Earth even if you're way up in the air. Electrical forces can be field forces, and magnetic forces are another good example of a field force. Free body diagrams are a way to kind of draw out forces that are acting on things. So forces are vectors, and so they can be drawn with arrows, just like all the other vectors we've drawn. And the size and the direction of the arrows really does matter. You know, the size of the arrow tells you the magnitude of the force, and the direction tells you, yeah, you guessed it, the direction of the force. So free body diagrams analyze forces acting on a single object or a system of objects. Forces that do not act on the object or system are not drawn. The first force I'd like to discuss is the force due to gravity. This force is pretty much constant on a planet. Force of gravity can be abbreviated by F sub g, force due to gravity. The gravitational pull of Earth on an object is also known as weight. So if we say weight, we mean the force due to gravity. On a free body diagram, you would draw it straight down. So there is a, we'll call it, this red block we'll be using a lot, we'll call it a brick. There is a picture of the force due to gravity straight down, right? Force or weight. The second most common force we'll discuss is probably a force you haven't really heard about before this class. It's the normal force. F sub n is how we abbreviate normal force. The normal force essentially is just the force that supports you or supports anything, right? So like the force coming from the floor or a table or a road. Now a free body diagram, if you're drawing the normal force, you draw the normal force perpendicular to the support surface. So it's not always up. Like here's that brick again sitting on a flat floor, and you can see that the normal force is up. But real quick, I want to just say, let's see here, grab a pen real fast. If the floor, let's say that red brick was sitting on a hill. Well, then the force due to gravity would still be straight down, but the normal force would be perpendicular to the surface. So this would be force sub n. So keep that in mind. The normal force is not always straight up, but gravity, however, is always straight down. The third force I'd like to talk about is friction. Force due to friction, we will abbreviate that F sub F. And it's a force that generally opposes motion through contact. In a free body diagram, you draw friction in the opposite direction of motion. So if something's moving, friction's going the other direction. There you go. So let's say, apparently, if the force due to friction is going to the left like that, that means this block, this brick, must be sliding to the right. And of course, because the force due to friction is the only force in the x dimension, if this block is sliding to the right, it must be slowing down, and we'll get to that a little bit later. Now, an applied force is exactly as it sounds. It's a force that's applied to something. We could abbreviate that F sub A. And it's any generic push or pull. Usually we'll be a little more specific than saying applied force. We'll say like force due to a baseball bat or force due to tension or whatever. But just a general thing, we could say it's an applied force. In the free body diagram, you draw it in the direction that the direction of the force, the direction of the push or pull. So now, if we got this brick, the force due to friction is to the left. The force applied is greater than the force due to friction. And so this object would be speeding up to the right. Tension is another force. Force due to tension, abbreviated F sub T. It's a pulling force caused by a rope, a string, a cable, a chain, whatever. Free body diagrams, you draw the arrow along the cable or the string that's supporting the object. So you've got the force due to gravity straight down, the force due to tension up. This is clearly a different red brick, and it is just being supported, and it looks like the force due to gravity and the force due to tension are the same. They have the same magnitude, And so this object has a constant velocity, which could be 0. Next force we'll discuss is air resistance. Now, typically in physics class, we say that, hey, there's no air resistance for this problem, and that's because, well, we haven't known what to do with two forces yet. There still will be a significant amount of problems where we say ignore air resistance, but now we're going to be able to work with air resistance. Air resistance can be abbreviated F sub air. It's a type of friction caused by an interaction with the air. Essentially, whenever anything moves within air, in order to move, you have to displace the air that was there before, and that causes a force. And actually, the air resistance, the force of air resistance increases the faster something is going as well. So in terms of a free body diagram, it's drawn in the opposite direction of motion. So there's a skydiver. You can see that the air resistance is going up and force due to gravity is going down. So what is a net force? Is it a force caused by a fishing net? I'm sorry, that was a horrible joke. No, the net force, we can abbreviate it F sub n, and really it's just the sum of all the forces that are applied on the object. So if I've got this situation here, where it looks like I have, this must be, maybe that's the force due to gravity, maybe that's the normal force, maybe this is the force due to, let's call it friction, and then this would be a force applied, we'll say. Well, it looks like in the y dimension, right? If I'm going to, what are the sum of the forces in y would be, it would be the normal force plus the force due to gravity, which is negative 500 plus 500. You know, now that I look at that, that seems a little awkward. I would probably put the negative somewhere else. However, whatever. And that's 0. So you can see that the forces in the y dimension, you wouldn't need to write all that out, right? I mean, you can see the forces in the y dimension, they cancel out. They're equal, right? And the forces, the sum of the forces in the x dimension, it looks like we have the force due to friction plus the force applied. And that would be negative 110 plus 350, right? And so you end up with this, the sum of your forces is, what, 240 newtons. So 240 newtons to the right. So there you go. So the sum of the forces, all you got to do, add all the forces up, and that's the sum of the forces. So let's look over this little practice problem here. We got an elevator is suspended by a cable. It's moving upwards and slowing to a stop. Which free diagram is correct? So I'd like you to pause the video and just think it over and try to come up with an answer now. All right, thank you for pausing it and trying that. So I'm going to talk about each answer, and we'll see if we can get ourselves to the correct answer. So the most important thing to know is that the elevator is moving upward, but it is slowing to a stop. Now, if the sum of the forces causes acceleration, okay, so the sum of the forces, if it's slowing to a stop, so I need to figure out, well, what direction is acceleration, right? Well, if something is slowing down, we'll remember that that means acceleration is the opposite sign of velocity. So the velocity is up, and it's slowing down, so that must mean the acceleration is down, okay? Which means the sum of the forces should be the sum of the forces is down. That's what that means, because the sum of the forces, the sum of the forces will cause acceleration if you have something that's not 0. Okay, so this looks like right here, it looks like this is equal forces, right? So the sum of the forces here looks to be 0. and therefore this object is not accelerating. Okay? It's, well, you know what? I think I'm wrong, actually. I think the sum of the forces is up, isn't it? This may be a little bit longer. It's kind of hard to tell. Either way, the sum of the forces is definitely not down, so that's not our answer. This one, yeah, these look equal, don't they? Yeah, so this one, the sum of the forces is 0, and therefore this object is not accelerating. So it's either moving up or down at a constant velocity, or it is stopped. But none of that means slowing down to a stop moving up. Okay? This one, it looks like the sum of the forces is down. Ooh, wow, that was weird. Is down. And therefore, it definitely could be slowing. It could be moving up and slowing down. This might be it. I think this is it. And this one has some weird extra force that doesn't actually exist. You're often going to be tempted to say that there's like a force due to the motion of the object. That is not true. The object is moving because it's moving. It's moving because it was moving before. It's moving due to its own inertia. But that is not a force that's being applied to the elevator. It might cause a force if it ran into something, but that's not the case right now. So it looks like the option is C, or the answer is C. Next few slides, we're going to do some practice problems. So I'm going to just show you an example problem. I want you to pause it, try it on your own, and then start it up, and I will talk about it. So pause it now. Try it. All right, thank you for trying that. Let me do this. So a rock is in someone's hand. So I'm going to draw a rock. Now, it looks like there's pretty much, if you can assume the object is on Earth, then you can assume the object is undergoing a force of gravity. And then since it's in someone's hand, the hand is that's supposed to be straight up. You can imagine that's straight up. The hand is applying a normal force. And these two vectors should be the same because it doesn't say the rock is accelerating in any direction. So that's how that one goes. All right, so now why don't you pause it and try this problem. Thank you for doing that. Now, let me try this out. A hockey puck is sliding across the ice. So you got a hockey puck here. And it is sliding across the ice. Now, you have to ask yourself, is the hockey puck accelerating? Now, because it's ice, we can assume, usually when a physics problem says ice, we assume zero friction. Now, if you thought there was friction, you may have drawn friction, and that's fine. Or if you said, well, that's ice, we're going to assume zero friction. Essentially, in reality, there really is friction, even on ice. But in physics class, we kind of pretend there isn't. So the hockey puck would have a force due to gravity and an equal normal force. And if you've decided there is no friction, then don't draw friction. If you want there to be friction, I would say there's an optional force due to friction. You are not wrong if you drew the force due to friction, but I think in the future when there's ice, assume there's no friction. Okay, so it's time to try again. Pause the video and then unpause when you're ready. All right, thank you for trying that on your own. So we got an elevator. It's being pushed upwards by a cable at a constant speed. So when you see constant speed, you should think to yourself, that means there is no net force because there's no acceleration. So that means we've got a force due to gravity. And guess what? We have an equal force due to tension. And they should be equal because even though the elevator is being pulled upwards, it's being pulled at a constant speed. So that means there's no net force. There's never a net force if there's no acceleration. And that means zero velocity is no acceleration, but also constant velocity is no acceleration. All right, time to try another one. Pause the video and give it a shot. Okay, we got a rock falling off a cliff on this one. All right, here's a rock. Now, you may have drawn force due to gravity, and you may have said, in physics, there's no air resistance unless my teacher tells me there is, and I'm done. And that's valid. Or you could say, you know what? there is air resistance. Either one is fine by me as long as you kind of told yourself and you thought about it. It's all good. So we just have those two forces, and that's it for that one. Okay, try another one. Pause the video and give it a shot on your own. Okay, so we have a skydiver falling through the air at terminal velocity. All right, so here's the backpack, whatever it is, the parachute. All right, so we have gravity. And terminal velocity means that air resistance is equal to gravity. The force due to air is equal to the force due to gravity. And that means that this skydiver is no longer accelerating downward. The skydiver is going really fast, but at a constant velocity downward. So what is equilibrium? I think you may remember that from chemistry class, but in physics it's a bit different. So equilibrium is the state of a body in which there is no change in its motion. And it does not necessarily mean at rest. I mean, it can mean at rest. If you're just sitting there not moving, there's no change in your motion, but there's also no change in your motion if you're going at a constant velocity. And if something is at equilibrium, it means that all forces are balanced. The vector sum is 0. So the sum of the forces in x is 0, the sum of the forces in y is 0, the sum of the forces in z is 0. And we won't really talk about z yet, but there you go. And the net force is 0. So an object in equilibrium has a constant velocity. Okay, it's really important. But it's important to know that constant velocity can mean 0 velocity. It can also mean some non-zero velocity, which is a constant velocity. So I'd like you to maybe pause your video or come up with your own answer to the next few questions. So question 1, can an object be in equilibrium if only one force acts on it? How about 3? How about 19, right? Go ahead and come up with your own answer for that. All right, so if there's one force acting on an object, there's actually no way for it to be in equilibrium. Because one force means, well, how is the sum of the forces going to be 0 if there's only one force acting upon it, right? And it can't be. Right? There'd have to be some force counteracting that force in order for the sum of the forces to be 0. Now, if there's 3 forces acting on it, well, now that is possible, right? You could have like maybe 2 forces in the opposite direction, and those forces add up to the same sum as this one. Or you could have a situation where you have 3 forces all kind of in opposite direction. I don't know if I do that very well. But there is a way where you could imagine that the vectors, if you added up all the vectors and x and y, the x and y components of all these vectors, they ended up being 0. I don't know if I drew that perfectly, but there is a way to do that. And if there's 19, sure, why not? Why not? Just all different directions, and somehow the x and the y components add up to 0. That's definitely possible. Why don't you come up with an answer for this one? If a car is traveling westward at a constant velocity of 20 meters per second, what is the net force acting upon that car? So the key here is it says constant velocity. The car's traveling at a constant velocity. Constant velocity means no net forces. You only have a net force if you have acceleration. How about this one? If a car is accelerating downhill under a net force of 3,674 newtons, what force must the brakes exert to cause the car to have a constant velocity? Okay, so the answer to this one, guess what? The brakes will be completely the opposite direction. They'll cause a force that's in the opposite direction of motion. And if you want a constant velocity, the brakes need to apply the same force. So it's the exact same force, but in the opposite direction. So the force would be negative 3,674 newtons. Let's review a little bit. So recap of Newton's first law. Balanced forces will cause an object to stay at rest if it's at rest, or stay in constant motion if it's in constant motion. Newton's second law. Unbalanced forces will cause a mass to accelerate. And this is the important one here. Here's our equation, which we've talked about a lot but haven't formally written out. The net force equals mass times acceleration. So when we did that simulation lab, we had the puck being pulled by a string, and we could change the force applied to the puck. We found that acceleration is proportional to force, right? That seems to be what this graph is showing. We found that acceleration is proportional to the inverse of the mass, right? All right, so so I've got acceleration is proportional to force, and I have acceleration is proportional to 1 over mass. Well, if I want to combine this and just into an equation, and here's the good news, since I've got nothing on my origin right here, I don't really have to worry about any kind of y-intercept or anything when I make an equation. It's actually pretty logical to say that, okay, well, acceleration must just equal force divided by mass, right? Because look, that means that acceleration is proportional to force, and that means acceleration proportional to 1 over mass. This equation means both of these things. And if I just rearrange this, well, then I could say that force equals ma, which is the most used equation, or I mean, essentially, the sum of the forces is ma, right? We could say the sum of the forces, because with the experiment we did, we only had one force. So that's kind of how we derive that equation based off of our lab data. So Newton's second law, like other two-dimensional problems, it's easier to break it down into components, right? So the sum of the forces in x equals mass times acceleration, and the sum of the forces in y equals mass times acceleration. I suppose I should say acceleration in x and acceleration in y and be a little more specific there. And then the net force equals mass times acceleration. So the object will accelerate in the direction of the unbalanced force, right? So essentially, we're really just adding one equation to all the stuff we already know. We already are very acquainted with acceleration. And mass is a pretty simple thing to measure and find. And so we add this equation to everything we already know. And it's going to end up being pretty logical. It makes more sense if I show you some practice problems. So if you push something forward, it's going to accelerate forward. That's kind of the easy way to put this. All right, so Newton's third and the final one we're going to talk about, it's the law of interaction. Forces exist in pairs. So for every action, there's an equal and opposite reaction force. And the forces act on at the exact same time, but on two separate objects. For example, a hammer hits a nail, the nail hits the hammer. Because they act on different objects, they're not going to cancel each other out. Okay? What's important about this is to know that you're always going to have two exactly opposite things. So like if you punch something, let's say you punch a couch. Let's make it something easy. But you are going to hit the couch with the same force that the couch hits you. Okay? I don't know if you ever hit something or like maybe slapped a table. You can hear the table gets hit, but it also hurts your hand a little bit. So the very, very important point to keep in mind is that the forces, when two objects come into contact like that, or any force for that matter, it's always going to be applied to two things, and it's always equal and opposite. All right, so one more everyday force we haven't really discussed, weight. Weight is the magnitude of the force of gravity acting upon an object. Force of gravity equals mass times the acceleration due to gravity. And here's the thing. This is really no different than saying force equals ma, right? Because the force due to gravity, the force that you are applying to the Earth, is just your mass times negative 9.8 meters per second squared, right? That's all it is. So you take the mass and you multiply it by the force due to gravity, and then you get the force, you take the mass and you multiply it by the acceleration due to gravity, and you get the force due to gravity, okay? It's quite important. There's going to be a lot of times where I give you the mass in a problem, and if you think to yourself, mass is the force due to gravity, you will not get to the right solution on that problem. You have to first take that mass, multiply it by 9.8, and then now you have the force due to gravity, or the weight of that object. So again, the gravity on Earth is negative 9.8 times meters per second squared. And the weight varies with location because the acceleration due to gravity varies, right? Things accelerate slower on smaller bodies like the moon than they do on the Earth, and they accelerate faster on larger bodies like the sun or one of the larger planets. Now, mass does not vary with location. It's just the amount of stuff within an object, right? Mass is determined by the amount and type of atoms that make up an object. All right, so next the next time I have a lecture, we will get more into the weeds about friction and how to calculate friction. But this is it for now. Thank you for sticking with me. Talk to you soon.